right, folks, this is it. This is linear relations. This is probably the starting point of most of the new high school math content. This is going to be stuff that'll build into what's carried into grade 10 and grade 11 and grade 12. So relatively new stuff. Linear relations, they are they're a big focus of grade 9, grade 10. So it's important to kind of develop an understanding of what's going on here. So what we're looking at is relations or relationships, which are, by definition here, just a pattern formed by two sets of numbers. So we're going to be comparing two things. There's never just going to be one thing. It's never just going to be the speed of people. It's going to be the speed versus the distance they traveled, or it's going to be the number of minutes you used your cell phone versus the cost, and probably most of you have unlimited plans now, so it's probably like the number of the amount of data you use versus the cost that you had to pay, unless you have unlimited data, and then it doesn't matter. But it's going to be comparing two things to each other. So this is what we're looking at when we're working with these linear relations, is comparing patterns, specifically patterns that are formed in the case that they will create a straight line when we graph them. So if we look at this relationship, I just did a quick example, and we'll look at some other examples of relationships in a moment. But here's an example. The amount of time someone practices, I don't know, hockey, and the number of goals scored. So you're like Wayne Gretzky, and you took, I don't know what it was, 400 shots a day, and the guy got like a whole whack load of goals. So the more time you practice, the more goals you get. And so this is the relationship. And if we look at this chart here, it's a scatter plot is what it's called, because they're kind of scattered around points. We see there is a relationship that the more time you practice, as practice time increases, the number of goals increase. So that's what a relationship is looking like in this case. And it doesn't have to be going up. It could be going down. It could be curved. If you've seen any of the graphs that are out there with the current pandemic, then you'll see that there are these kind of graphs that are going upwards and curving over. They are logarithmic graphs, which are a different type of relationship, or you may have seen them in an exponential form. And so there's different types of graphs out there, but that create different types of relationships. But in our case, we're looking at relationships where as one thing goes up, the other thing goes up, or as one thing goes down, the other things go down in a relatively constant manner. Well, not relatively, exactly constant. They should be going, linear relationships are going constantly up or down. So in our case here, if we take a look at the definition of linear relationships, graphically, if you plot these things on a graph, unlike this one here where they're kind of all over the place, the points will line up nicely, perfectly in a straight line. In a more formalish definition, each change in the x-axis being the horizontal axis or the independent axis variable. So each time this one changes on the bottom, the other one will change in a constant manner. And we'll look at some examples in a moment here of what that means. So that y-axis, the other axis is going to change proportionally, meaning the same amount each time. It's the y-axis, the dependent variable. It depends on what happens here. So the more you practice, the more goals you score. The more you score, the more goals you score doesn't necessarily translate to the more practice time that you have, per se. Thus, the goal scored is dependent on the independent practice time. And then the vertical axis variable is another term for that one. So this is a little more convoluted definition, but independent, horizontal, or x-axis, dependent, vertical, or y-axis. And as the idea here is with a linear relationship, as this one changes, so does this one. If this one goes up at the same amount, or if this one goes down by a constant amount. So we'll take a look at these and look at some examples, and that was probably a bad definition. But ways that we can show these different types of relationships. We can use sets of ordered pairs. So here's our x values. So this here, again, these are always ordered pairs are an xy, xy, xy. So x goes up by 1, x goes up by 1. When x goes up by 1 each time, the y value goes up by 3. 4 plus 3, 7 plus 3. So the x value is going up by 1, the y value is going up by 3. That is a linear relationship because the numbers are going up as x goes up at a constant value. As the x goes up by 1, the y goes up by 3. Every time that's what happens. In the case of number 2 here, we can show them via a table of values. Some people like to call this a T-chart because the 2 lines here look like a T. So what we do is we have our x values and our y values listed in columns, and each ordered pair matches up here. So if we compare this to our ordered pairs above, if x is 2, y is 4. x2, y4. X is 3, y is 7. And so each ordered pair matches up. So each of these left-right pairs of x, y, these are ordered pairs. Taking a look at these and comparing these, what we have is that the x value is going up in each case by 1. So we go up by 1, we go up by 1. And in the y value, that again, linear idea that the y value is proportional. So if x goes up by 1, y goes up by 3. X goes up by 1, y goes up by 3. So if we were to imagine that we're going to expand this, extrapolate on this data, the next value in the x column would be 5. So the next y value would be 3 more, or 13. The next x value would be 6. The next y value, again, would be 3 more, or 16. So we can kind of extrapolate on that because there's a pattern that's happening, this constant pattern of when this goes up by 1, this goes up by 3, and that is how we generally define our linear relationships. A change of 1 in x, how much does y change for every 1 change in x? The next type or way of showing the relationship is a graph, and we looked at it as a first example. So here I have a linear graph. Each point I go over and up and over and up and over and up, and these are a constant kind of staircase of steps up, and you would extrapolate that and you go over and up and over and up, and you'd have the same kind of pattern. This horizontal distance each time would be the same, and for each horizontal step over, you'd go the same vertical distance up. And we'll look at this more as we kind of get into concepts of slope and things like that. But for each constant horizontal change, there's a constant vertical change. And then the other way that we generally look at these is we use an equation. So the relationship, and in general with linear equations, and most of the equations we'll work with, because the y value here depends on what the x value is, it'll be y equals. So in the majority of our cases, we're going to work with y equals. It may be rearranged in other ways depending on the certain situations, but in general, y equals is our kind of standard format of writing these. And so y equals, 3x minus 4. So what happens is, whatever value x is, we can figure out a y value, and it's going to be constant. So I can make a little table off of this equation really quickly. If I wanted to. So I can make x and y, and let's just pick easy numbers, 1, 2, 3, and 4. So if x is 1, 2, 3, and 4, y equals 3 times 1 minus 4. That's our x value. That's the relationship between x and y. So 3 times 1 is 3. 3 minus 4 equals negative 1. So that's our first y value. The next one, 3 times 2 minus 4. 3 times 2 is 6. 6 minus 4 is 2. The next one is 3 times 3 minus 4. So notice each time I'm just replacing the x value with the value that I've listed here. So 3 times 3 is 9, minus 4 is 5. And then the final one, 3 times 4 minus 4. 3 times 4 is 12. 12 minus 4 is 8. I'm going up in each case here. 3 jumps, plus 1, plus 1, plus 1. Over here, plus 3, plus 3, plus 3. So I'm just jumping up by 3 each time. So for every increase of 1 here, I'm jumping up by 3 here. Is it always 1 and 3? No, it just happened that I picked these numbers that worked out that they're 1 and 3. But you can take that equation, you can create yourself a t-chart from that equation like that. Now for an example with a question that we can work with on this general idea, this here. So what we have is that a hot air balloon is flying at 600 meters above sea level. It slowly descends at a rate of 50 meters per minute. So we're going to do a little bit of work with that now. So we're starting with creating a table of values to show the height of the balloon for the first 6 minutes of descent. So creating a table of values, or a t-chart, requires us to make a set of columns. I usually just make a nice simple T here. So there's my T. And I'm going to label it X and Y. Okay, and I'm just going to note over here, X equals the time, and Y equals the height. Okay, we could use T and H, but I think sticking with X and Y here initially is a better idea, just to give you guys a good understanding of the X and Y concept with these linear relations. So we want a table for the showing the height of the balloon for the first 6 minutes of descent. So at 0 minutes, the height of the balloon is going to be 600 meters. So it's going to start at 600 meters. And then after 1 minute, it's going to go down by 50 meters. So it's going to be down at 550. Then the next minute, it's going to go down another 50 meters to 500. The next minute, it's going to go down another 50 meters to 450. And then to 400. And then to 350. And finally to 300. So over the course of the first 6 minutes, there is a t-chart illustrating this linear relation where it's constantly going down at that rate of 50. So each one of these, we increase 1 minute plus 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 1 minute. So each of these, I can even illustrate that, plus 1, and so on. Here we are going down 50, so minus 50, minus 50. And we continue our way down. So now we want to graph this information in the next part. So we're going to take that table, the values from the t-chart, and use those to create ourselves some ordered pairs. So the highest value on my graph here was 600. So I'm going to figure out, this is the graph that I have made myself. So I got to make sure that I'm going to fit things in here. I'm actually going to do what's called a broken graph. So I'm going to start at 0, but I'm not going to go from 0 to 600 and evenly space them. I'm going to break the graph right here and jump up. So I'm just going to put a little kind of thunderbolt through there to show that I'm breaking the graph. And so for my heights, I got 1, 2, 3, 4, 5, 6, 7 spots there. So I could even start my graph up here. I'm gonna start with 650 just to give it a little extra space. Then 600, 550. 500, 450, 400, 350. Maybe I should have done it the other way. Yeah, should have done it the other way. Let's change that up. So we'll start the graph at 600 so it all fits. 600, 550, 500, 450, 400, 350, and 3,500. Too many zeros. 350 and 300. There. So now I have my graph. I got a scale, and again, that break there says, you know, we're jumping from 0 to the 300. So we always do that if 0 would be a value that we're working with, and we're going to jump ahead. So this allows us to jump to 300. So that'll get us all these Y values. So my X values, 0, 1 minute, 2 minute, 3 minute, 4 minute, 5 minute, 6 minute, even 7 minute could be on there. So this is the time. And over here, I have the height. So I got a time and height. So my time is on the x-axis, my height is on the y-axis. So I got my graph all set up. Now I can plot my points. So my first point is 0 and 600. So 0 on the x-axis, 600 on the y-axis. Remember, we always read them x, y in that order, and we graph them x, y. So 0, 600 is where the x and y match up. The next one, 1 and 550. The next one, 2 and 500. Then 3 and 450. 4 and 400. 5 and 350. And 6 and 300. Now, ideally, I've drawn my grid lines nice and evenly spaced, which they're fairly accurate here. I should be able to connect these dots neatly, and they're not perfect, but it's not going through the middle of all of them, but that is approximately a good looking line. I could actually extend this line all the way down to the end here. So there is a graph, a linear graph of this relation. So it is a linear relation because we have a line. So is this a linear relation? Yes. The graph is a straight line through all the points. Okay, so it's a linear relation because the graph is a straight line through all the points. If one of these points, say for example, this one was right here instead of here, so say we move this one up to here, then that wouldn't be a linear relation anymore because the balloon would have started going back up again. So that is not going to be accurate. And if you do accidentally put a point on a graph and you do it like me in pen and you don't want that point there, you can just put an X through that point. And then when we're looking at assessment net, we usually know that we're not marking that one. So there's our linear relation as a t-chart, as a graph. So the question, next question here says, does the graph increase or decrease? And so when we're talking about increasing or decreasing, we're talking about how is it going as we move from left to right. So from left to right, the graph is, and so from left to right, we're decreasing in value. The y value is decreasing from left to right. So it's a decreasing graph. And the important thing here is that as we move from left to right, that we are doing this. So as we're moving from left to right, we have a graph that's decreasing. We only read it, our description of increase or decrease as we move from left to right. So the last part here, and I forgot to write the actual question down, but what is the height of the landing space if the balloon takes, let's say, 9 minutes to descend. So we want to know the height of the landing space, whatever it's landing in, if it takes 9 minutes to descend. So we could, if we had a bigger graph, we could have continued and taken that down, but we don't go far enough on our graph to 9. We could extend our t-chart here to 9. I don't have any room there to do that. So I'm going to do another form of representing an equation, or sorry, a linear relation, and that's an equation. So the height, which is y, at any time is equal to 600, our starting height, right? We started at 600, minus 50 times the number of minutes, or times t. So 600 minus 50 times t, and I'm going to change that. That should be, let's rewrite that. We were using x and y. So y equals 600 minus 50x. So the number of minutes it takes, 1 minute, 600 minus 50 times 1 would be 550. So that works out. So that's our formula that we would use. So if it takes 9 minutes to descend, all I need to do is substitute that x with 9. So 600 minus 50 times 9. And when I do that, 50 times 9 is going to be 450. And then I can subtract those. Y equals 600 minus 450, or 150. So the landing pad is 150 meters above sea level. So again, I made that equation by looking at where did I start from. I started here at 600, and then I was going down by 50 every minute. So 600 minus 50 every minute is how you would look at that equation. That will give you your height, which was the y.